Thank you for having me at PyData. It's great to be here. So my name is Zack. I'm a machine learning engineer at Atrium. Atrium is a legal company. It's a law firm based in San Francisco, and also happens to employ a lot of engineers, of which I'm one. You might be wondering, why does a law company need to have all these engineers? And the answer is that Atrium's goal, as shown in this Washington Post article, is to replace lawyers with robots. OK, I'm just kidding. That's not actually the goal. That's like the hype version of the goal. The real goal of Atrium and the engineering team at Atrium is to save time for lawyers and paralegals, make them more efficient at their jobs, help them to do their jobs better by automating some of the boring, rote stuff that they have to do every single day. So the area that in particular that we're working on right now is intake. What intake is let's say you're a client of Atrium's, right? So you sign up with us. You're a promising young startup, and maybe you're switching from your old law firm that you don't like very much, and you have a whole big zip file of legal documents, which could be anything. It could be your employee contracts. It could be your board consents, your stock purchase agreements. It could be your old bank receipts, anything. You got 1,000 of these documents. You send them all to Atrium, and we have our paralegals go through every single document. When I say we do, I mean we used to before the ML team did its thing. And this is what happens at big law firms now, is that it goes ships to the paralegals. They have all these documents. They have to go through each and every document and figure out, OK, what type of contract is this? And who's the investor? How much should they invest? What's the date that the contract was executed? All this stuff. They have to open each document individually, scroll through, try and find where the information is in the document, copy it, paste it into an Excel spreadsheet. And it's pretty time-consuming, and it also doesn't really utilize any of their legal skills that they went to school to develop. And overall, it takes them about 2 minutes per document. They go through about 30 in an hour. So what the ML team is doing at Atrium is we're automating some of this stuff, and we're having an algorithm go through and look at the documents and make guesses about which parts of the document represent the investor name, which part represent the discount rate that the investment is at, all that kind of stuff. Now, these are not zero-touch models. What I mean by a zero-touch model is a model that is always right 100% of the time. That's not really how machine learning works, right? There's always some kind of error rate. And we can't really afford that in the legal world. We have to be very accurate. So instead, what the model does is it'll make guesses. You input a document, and it'll say, OK, we think that this is the interest rate. We think that this is the investor. And we pass that along to the paralegal so that the paralegal can quickly accept the suggestion or reject the suggestion. You can draw an analogy here to the P versus NP problem, where it's a lot easier. This is for my computational complexity people out there. It's a lot easier to verify a solution than it is to find the solution yourself. Like if someone gave you a huge prime number, you'd be hard-pressed to find what the factors are. It's super hard to do. But if somebody told you, I think the prime numbers are this and this, it'd be pretty simple for you to multiply those together and see if they were, in fact, the prime numbers that multiply to make the number. So we make these guesses, and the paralegals check whether the guesses are right or not. And if it's right, then they can just quickly accept it. Saves them a whole bunch of time. And as a team, we're down to we can actually do 150 documents in an hour now, which is a big increase from the 30 that we were doing prior to the introduction of these techniques. So how does the algorithm do all this cool stuff? The model that we use is called a conditional random field, or CRF for short. And it's kind of similar to a hidden Markov model, if you've heard of those, except that it's discriminative instead of generative, and it makes fewer independent assumptions. If you don't know what hidden Markov model means, you don't know what generative discriminative means, please do not worry. That's what this talk is going to be all about. And one more thing before I start getting into the math, which is that if you have any questions about something I'm saying, then please raise your hand and ask during the talk, because there's probably a lot of other people out there that have your exact same question. All right. So before we get into the actual legal document aspect of it, we're going to take a detour to the world of the 2000s movie Disturbia, starring Shia LaBeouf. I hope I pronounced that right. And in this movie, he plays the role of an angsty teenager who is confined by an injury to his house. and he can't actually go outside, all he can do is look out the window and see what his neighbors are up to, basically. So we're going to pretend that we, collectively in this room, are Shia LaBeouf, and we're going to try and predict what the weather is outside. We're going to try and predict whether it's rainy or sunny, but we can't actually see the weather because we're housebound. All we can see is whether our neighbor is carrying an umbrella or is not carrying an umbrella when they leave the house. So to simplify things, we're going to assume that there's two states that the weather can be in. Either it's sunny in a certain day or it's rainy during that day. And we're going to assume that it doesn't change during the course of a day. In any given day, it's either sunny or it's rainy. And what this means is that there's 4 different transition probabilities between the states. It can either go from sunny to sunny or sunny to rainy. With some probability, it can go from rainy to rainy or rainy to sunny. And to make the math a little bit simpler, we're going to assume that the weather always stays the same with probability 3/4 and always changes with probability 1/4. So 3/4 of the time, if it was sunny today, it'll be sunny tomorrow. 1/4 of the time, it's going to flip. Now, given this information about the transition probabilities between the states, what we're going to try to do now is we're going to try and calculate the probability of a specific sequence of 3 different states across 3 different days, given what the weather was on the starting date. So we're going to assume that it was sunny on day 0. Now let's say we don't look at days 2 and 3 on this board, but we're only looking at day 1. Given that it's sunny on day 0, anyone have any guesses about what the weather is going to be like on day 1? Sorry, what are the odds that it will be sunny? Nice, 75%. Cool. So that was easy. Now it's going to get a little trickier. Given that it was sunny on day 0 and day 1, now we want to look at day 2, bring that into the equation. So what are the odds that it's sunny on day 1 and sunny on day 2, given that it was sunny on day 0? I heard 75 times 75, which is exactly right. What we're going to do is multiply the 0.75 by the 0.75. End up with 56%. Now, the reason that it's OK to do this is the conditional independence of day 2 and day 0, given our knowledge of what the weather was like on day 1. So I'm not saying that day 0 and day 2, the weather on those 2 days is independent, because it's not independent. If you know that it's sunny on day 0, that tells you something about what the probability is likely to be on day 1. If it's sunny on day 0, it's probably going to be sunny on day 1. If it's sunny on day 1, it's probably also going to be sunny on day 2. So knowing what the weather is like on day 0 does actually give you some information about what the weather is going to be like on day 2. But given the knowledge of what the weather was like on Monday, now the weather on day 0 is independent of the weather on day 2. And that's because all the information about the sunniness or lack thereof on Sunday sort of got encapsulated into what the weather was like on Monday. We only cared about what the weather was like on Sunday insofar as it told us that it was more likely to be sunny on Monday, which then told us that it was more likely to be sunny on Tuesday. But once we sort of interrupt that chain by being given information about what it was like on Monday, now the probability of sunny Tuesday and sunny Sunday are actually independent. All right. So now that we know that we can do that, how do we get then the combined probability of all of these 3 different states from sunny to rainy? What are we going to do? Just shout it out. Multiply by 0.25, and we end up with a 14% probability of having this exact sequence of states. And these sequence of states are what we care about getting the probability of. These are later, the analogy is going to be that these hidden weather states are going to be like the hidden states that are determining whether something is investor name or not. Now we're going to bring the observations into it, the disturbia part of it. And here are the 2 observations that we could make about the weather, about the umbrella status of our neighbor. Either they have an umbrella or they don't have an umbrella. Those are the 2 observations that we could see. And these observations the probability of our neighbor either having an umbrella or not having an umbrella is determined by the weather. So we're going to assume that when it's sunny, our neighbor, being a reasonable person, usually does not have an umbrella, although some of the time they do. Maybe it's just a fashion statement. And when it's rainy, we're going to assume that they bring an umbrella 50% of the time and don't bring one 50% of the time. So these are the probabilities of seeing these observations given the underlying states, which, by the way, the fact that the states are hidden and that we don't see them, that's where the hidden and hidden Markov model comes from. So these are the probabilities of the observations given the states. What we want to use these to find is the probability of the underlying states given the observations. Since that is where we're at, we don't see what state the world is in. We just see these observations. And we want to infer what the probabilities of the states are given these observations that we made. So to help us do this, I drew out this nice schematic diagram where I labeled 10 sample days. We took 10 sample days where it was sunny, and we took 10 sample days where it was rainy. I should probably keep this on for mic purposes. And I put an umbrella next to there if we saw an umbrella that day, and I put no umbrella if we didn't see an umbrella. So because of these 1090 figures, you can see that there's one day where it was sunny and a person had an umbrella, and there was 9 days where it was sunny where they didn't have an umbrella. And on the 10 days where it was rainy, they had an umbrella 5 out of those 10 days. And those are like what we would expect to see on average given these probabilities. So using these numbers, finding the probabilities of the states given the observations is now as simple as just counting. If we look at the total number of days where there's an umbrella in this picture, can you guys see this, by the way? Cool. You can see that there's 1 day where there was umbrella and sun, and 5 days where there was umbrella and rain, which means that given that we see an umbrella, the odds that it were sunny is going to be 1 out of 6. We can do the exact same thing to get the probability that it's raining or sunny, given that the person doesn't have an umbrella. And we see that there's 14 total of these cases where the person did not have an umbrella on a certain day. 9 of them it was sunny, so the odds that the underlying state is sunny given the observation of no umbrella is 9 out of 14. What's interesting about this is that when it's raining, they have an umbrella 50% of the time. So you might think that just because they have an umbrella or not, that doesn't give us any information, because when it's raining, they're equally likely to have an umbrella or not have an umbrella. But the key is that when it's sunny, they're very likely to not have an umbrella. So them not having an umbrella serves as evidence that it is sunny outside. Now, this is not a causal relationship. It's not like when our neighbor carries around an umbrella that actually makes it more likely to rain. That's not what's going on. Some people think it is. Like that's basically what superstition is reversing the order of these effects. Yeah. Or if you don't bring an umbrella, then like for sure it's going to rain that day, right? Because it's the day that you forgot it. So yeah, there's no causality going on here. It's not like what we see about this umbrella is determining whether it rains or not. But despite that, there's still this probabilistic link between the two that allows us to make guesses about what the weather is. We've kept it pretty simple so far, and we've kept it to just one observation, umbrella or no umbrella. But that's by no means necessary. And we can actually look at multiple different observations. Like we might notice that our neighbor is wearing rain boots or sneakers. That could give us some information about the weather. And we might notice that they have a skeleton, that we feel it in our bones. Wait, I'm a little bit out of order on these slides. Hold on. Here we go. Yeah, so if you feel it in your bones that it's going to rain, that could be another example of an observation that is telling you some information about the weather that you can then combine with your other observations and get a combined probability. So skipping back a little bit, before we were just looking at 1 day at a time. Given some observation on 1 day, what are the odds on that specific day that it was rainy or sunny? Where it gets a little more interesting is when we have a sequence of 2 days. So here's 2 observations that we made. On Monday, we looked out our window and we saw that our neighbor had an umbrella. And on Tuesday, we looked up, we saw they didn't have an umbrella. And now what we want to figure out is, what is the most likely underlying sequence of states that gave rise to these 2 observations? There's 4 possible sequences, right? It could have been rainy, could have been rainy then sunny, could have been sunny then sunny, could have been sunny then rainy. There's 4 different possibilities for what the states could have been. We want to figure out what the most likely sequence of states was. What did you say? I love that you said that, because if we're looking at the days individually, the most likely choice on the day where they had an umbrella, we just calculated this, and we found that on the days where the person has an umbrella, there's a 5/6 chance that it's raining. So if we're just looking at Monday in isolation, we think that he probably had an umbrella, or we think that it was probably rainy on Monday, and we think that it was probably sunny on Tuesday because most of the time when there's no umbrella, it was sunny. And that's a great first intuition to have, but it does ignore one very important feature of this model that we've set up. Exactly. It's not likely to transition between these states. We have this prior knowledge that the weather is usually staying the same. And because of this, we're predisposed to believe in underlying sequences of states that don't have a lot of transitions between different weather types. So I'm not going to go through the exact math in getting these numbers, but I will footnote it by saying that if you want to know exactly how these numbers get calculated, you should Google forward-backward algorithm or a Viterbi algorithm. You can find some cool animations online. But for now, you can just take my word for it that it's more likely that the states went rainy then rainy rather than going from rainy to sunny. And the reason for that is we just don't really believe that it's that likely to change over. So we're biasing ourselves towards explanations that don't involve a lot of changeovers. Cool. Any questions up to now? All right. In that case, we will talk about how these numbers got arrived at. In this example, I was sort of the omniscient narrator, and I told you all what the chances were of these transitions between states, and I told you all about what the probabilities of the observations were given the underlying states. In the real world, we don't have this voice telling us what all the probabilities are. And this is where the labeled data comes into the model. So we have a bunch of paralegals on staff that have annotated a bunch of documents in the past, and they've said where all the, in weather world, it's like we had a meteorological history of the area, and we took notes historically of how often the weather was to transition between these states. And we've kept careful notes, and we've written down what exactly was going on with the umbrella on each day. And we used that to find out what these question mark percentages were. And no model is complete without data, so this is where the data enters this model. And being done with weather, we're going to move back to the English language. And the analogy that we're going to make here is that the weather, this underlying state of the weather, which determined these observations that we saw, which caused the person to have an umbrella or not, the weather is going to be what part of speech a sentence is in at any given time. And then the observations, the umbrella part, is going to be what word gets emitted. So you can think of a sentence as moving from part of speech to part of speech. Preposition or PRP. I actually don't know what PRP stands for, but PRP to VBP to a verb to a determiner, et cetera, et cetera. The sentence is moving from part of speech to part of speech. And what part of speech a sentence is in determines its probability of emitting a certain word. So let's take the word dog, for example, the 4th word in this sentence. It's possible that the word dog could be emitted by a verb state. It's possible that if the sentence is a verb right now, that we're going to see the word dog, because dog can be used as a verb. So the probability of dog given verb is non-zero, but it's not as high as the probability of dog given noun, because dog is more commonly used as a noun than it is as a verb. But both are dramatically higher than the odds of seeing the word dog given that we're at a preposition state, because I don't even think the word dog can be a preposition. So what this means is that in the same way as we are trying to predict the most likely series of states, given the observations before, given the weather observations, given these word observations, we're trying to predict the underlying sequence of parts of speech that gave rise to these observations. And just as we had multiple observations before, the umbrella and the boots, here, we're not just limited to looking at the exact word that came out, but we can also look at these other aspects of the word. So for instance, we can look at what are the first 3 letters of the word, or what are the last 3 letters of the word, or what is the previous word, or what's the next word. These are all different features that we can use. Features means the same thing as observations. In this case, I'm using them synonymously. And you can add your own features to this list. Like, I'm sure you guys could think of different features of a word. We have a bunch of them, and that's some of the main things that we work on, is just thinking about new features that we could add to this model that are going to make it more accurate. So here is an example of a legal document. This is just one paragraph of a legal document. It's not an entire legal document. But you can see it has a bunch of words in it, and we're going to try and figure out what the odds are, what the most likely series of states are that gave rise to these words. But we're not going to use all the different parts of speech, because we don't actually care at a law company whether people are using verbs or nouns. Rather, we're going to label most of the words in the sentence as O, which means that we don't care about them at all. They're just irrelevant to us. And then a select few of the words are going to be lucky enough to get their own label. In this case, we're going to try and label who's the investor and how much did they invest. And if the model did a good job, then what it outputs is going to look like this. Almost every word in the document is going to have a label of O. We don't care about it. But the 2 words that are part of the investor name are going to get their own label. So these things on the right are like the states. These labels, they're like the states. And then the words, these are like the observations. And this is an ideal world where the model worked as expected. A common error that we see in this amount is that it might miss the dollar sign, or it might miss a period. So it can actually get part of the answer right, but part of the answer wrong. And in those cases, when it's partially right or partially wrong, it's still useful to the paralegals, because it's still telling them where in the document to look. And that's why we are using this as a combined human and machine teamwork thing, rather than just letting the algorithm do it all on its own, because it's not going to be perfect. All right, we'll talk about some strengths of the CRF model. So some strengths are that you can choose whatever features you want to choose. You can really dream big with this. In fact, you can use like an entire other model just as input to this model. An example of this would be that we actually have a part of speech tagger. We use Spacey's part of speech tagger, and we run it over the entire legal document. And it gives us part of speech labels at each word in the sentence. Those words are then used as, those labels from the part of speech tagger are then used as features or observations for the root CRF that's making the predictions. Some other features that we use whether the word is a number or not. That's a really good one for knowing whether it's an interest rate or not. We have a list of months, and if the word is on that list of months, that's a good feature for the model to know about. We also downloaded a list of the most common baby names in the US and the most common baby names in the world, and that's a good feature to use when we're trying to predict whether something is an investor name or not. Now keep in mind that we're not inputting the weights of these features. We're not telling the model how much to care about whether a given word is an investor name or not. We're just telling it that it's something that it should pay attention to. In Shia LaBeouf world, this analogy to this would be like a telescope. like a tool that we can use that's helping us make these observations, but it's not actually telling us what the answer is. It's just giving us some input. So another strength of the CRF model is that it's relatively simple and doesn't have that many parameters when you compare it to something like bidirectional LSTM. Those types of models are more appropriate when you have tons of data, but Atrium is a pretty young company. I joined in May, it was 50 people. Now we're at like 130 people. We still have about 1,000 documents per document type, which means that using these smaller models is a little bit more appropriate than using a big model that's going to have a higher risk of overfitting, which, as we all know, is one of the cardinal sins of machine learning. Some weaknesses of the CRF model are that you have to hard code your features. If you use a fancy new shiny model, it's going to pick out all those features for you, and it'll do that sort of discovery work. And that has pluses and minuses. It can make it less interpretable, but it can also make it less work to do and more general. And another possible weakness of the CRF model is this assumption that the only thing that matters in these state transition probabilities is the states immediately before and after. So that whole thing about, if it's Sunday, if it's Tuesday, we don't care about what the weather was like on Sunday. We only care about what it was like on Monday. That's not really true in weather, and it's also not really true in English. It actually does matter what the weather was like 2 days ago, but just to make the model more computationally tractable and easier to execute, we're ignoring that fact and moving on. So I'm about to turn it over to questions. Before I do, quick plug for my colleague Jordan Bramble, who's going to give an awesome talk in about half an hour about some of the other cool work that we do at Atrium, including finding signatures and finding the absence of signatures in legal documents. And also, just to let you guys know, we are hiring. So if you go to atrium.co/PyData, you can see a list of all our super cool open positions. All right, that's it. Questions? Yeah. With word vectors? Yeah, we actually did. At the time that we experimented with word vectors, we built a bidirectional LSTM that used word vectors. At that time, we had a lot less data. We had only about 300 documents per document type. Something I didn't say in this talk, because I want to keep it quick, is that we actually built different models for each document type. Weather world, this would be like people are more or less likely to carry umbrellas depending on what state you're living in, or what the where you are, what your region is. So we have different models for each document type. At the time when we tried the word vectors and the bidirectional LSTM, we only had about 300 documents per document type. Now we're up to about 1,000, so we're sort of getting to the point where we want to explore using deep learning again, which is pretty exciting.
I mean, there's a lot of pre-trained models for that stuff.
Right. So yeah, we can use we didn't calculate the word vectors out ourselves. We took a list of word vectors that we downloaded from the internet and then used those instead of the words and then ran it through a bi-LSTM. Put a CRF on top, which is sort of the standard thing that you do.
Have you guys looked into comparing different legal documents and trying to find how similar they are, maybe?
Yes, actually. We did, because you might think that there's these templates for legal documents, right? Like maybe everyone who used prior law firm X, all their legal documents look the same, and everyone who used prior law firm Y, all their documents look the same. And that if you can classify them like that, then that'll give you a lot of input. But what we found is that the clusters that we tried to make weren't really that distinct from each other, and it didn't really work that well.
And when you did that, how did you vectorize the legal document? How did you represent that document?
I think we just did TF. It was actually another engineer on the team, but I believe we just used TF, IDF, and pretty standard stuff. Yeah. I should repeat these questions out loud. The question was, are these PDFs that we're using? Yes. So great question. They are PDFs. Sometimes they're .docs. But whatever they are, we send them all up to Google Cloud OCR, which then returns back a series of text. And in fact, along with the exact text of the document, Google OCR is also returning a bounding box around each word. And one of the features that we use is the location of that bounding box on the page. For instance, if you're high up on the page, it's more likely that you're an investor name because people usually put the name of the investor at the top. And also, what page you're on in the document can affect how likely something is to be a different thing that we care about. Yeah?
Have you tried out just regular expressions? I noticed in the example that you gave, there was a name, invested, dollar amount.
Yes.
Search on the dollar symbol or things like that.
Great question. The question was, have we tried using regular expressions? We found that that works pretty well for some document types. In particular, there's one called a SAFE, which is the standard investment vehicle that's used in San Francisco with Y Combinator, which is one of the biggest incubators. And we found that regular expressions work pretty darn well on a SAFE, and we used those for a while. But just recently, the performance of this model exceeded the performance of the regular expressions, so we've now switched over to using that. Yeah?
What about confidentiality? I mean, do these firms, they're like, sure, use our document to build your models, like, are they okay with that? Or?
Yeah, so we're all employed by the legal firm, and all the documents are strictly confidential, not seen by anyone outside the company. So if you're okay with a lawyer seeing your documents, and you're okay with a paralegal seeing your documents, then you're okay with an engineer who works at the company also seeing your documents.
Different firms are hiring you to go through the documents?
So Atrium is
I'm sorry. Yeah.
no, it's a great question. So the question was, are different law firms hiring us to go through their documents? So we're exclusively doing this on the data of our own clients. Because Atrium has this sort of unique profile where it's half a law company, half a legal company. The law firm, as its clients, it has different startups. And us, as the tech half of the company, it's almost like our clients are the lawyers. So we're building products to serve them.
So like company A doesn't mind that, or company B, they were both using their documents to build.
Right. And we're not sharing anything in company B's documents with company A. It's all just internal.
What about sending it up to Google or CR? I mean, how do you?
Do you want to say that louder?
Yeah, I think it's like you put it over the wire.
Okay. Yeah.
So you said that there are different document types. So do you guys do any sort of template matching that will automatically segregate the document types?
Awesome question. So the question was, how do we segregate the documents into these different document types so that we know which model to use? And we actually have a separate model that does that. And it's trained on different documents that have been labeled by paralegals. And that model is super accurate. That model is really almost at the point of being zero touch. It's about 93% of the time, our first guess is right. About 99% of the time, the correct document type is in our top list of 5. So yes, we have one model. We have this hierarchical system of models. The first model tells you which document type it is, and the second model does all the CRF stuff that we just talked about.
Do you speak the technology you're applying
To classify, yeah, it's straight up TF-IDF.
With what?
With the words that are in the document.
Oh, is it support vector machines or that's sort of modular conceptual?
So basically, like if we see that all the stock purchase agreements have the word stock and the word purchase, and then we see another document that has those words, and we're like, oh, it's probably the same one as the other document that had all these words in it. Yeah.
What kind of pre-processing do you guys do? Do you guys do some stemming, or you say you guys bring stoppwords, or you guys include stoppwords? What kinds of techniques do you use?
For pre-processing the text data to run these CRFs, we don't do any pre-processing at all. And that's kind of might be a surprise to some of you who are, if you've worked in NLP, you know that pre-processing is usually like a very important first step. The reason that we don't is that the stop words can actually be extremely important. And even the specific differences between a stemmed version and an unstemmed version of a word could have a lot of implications. That's also why word vectors aren't as effective as you might think, because just because two words like vaguely mean the same thing in the English language and are like similar to each other and used in similar contexts, that doesn't really mean that there could still be a world of difference in their usage in a legal context. Yeah.
Do you limit this exclusively to English language documents, or will you be able to generalize this to something written in like Spanish or
The model would probably still work if you trained it on Spanish or French documents, if you had enough of them. But I think so far, all of our clients' legal data has been in English, so we haven't had to deal with that issue yet. Yeah. How many document types we have? It depends how like low level you want to go into the genus. Yeah. Right. So we have, right now we have 6 document types that we have models for that cover most of our documents. But as we get more and more examples, we're going to keep training more and more document types. Yeah.
You mentioned that the documents from the same law firm won't be the same, but do you have any clustering, like, say, all the IP lawyers from LA do kind of the same thing, like by practice group or geolocation?
The question was if there's, if we can classify the documents by, like the nature of the client.
Yeah, by the practice group or like location. Everyone in LA does kind of the same thing. Everyone in the IP practice group kind of
Right.
does the documents the same way.
Well, most of our clients are Bay Area startups in San Francisco. That's like Atrium's official like mission is to be like the dominant legal startup for Bay Area, our legal company for Bay Area startups. So right now we don't have these regional differences going on. But once we expand into the furthest reaches of the world, then maybe we'll look into that. Yeah.
Do you guys have, well, in the industry, legal industry, is there any effort to standardize document types for digitization?
Yes. Great question. Is there any effort to standardize legal documents for like machine interpretation? Absolutely. And the SAFE, which I talked about, is like one of the first steps towards that. But if you achieve market dominance as a legal firm, then you get a lot of ability to set the parameters, and we would like to do that to make all of this a lot easier.
Is this something you guys offer with your clients, that all of your documents are obviously standardized, but that they have a hyper data component that also that can be easily extracted in space? So we work with your law firm or someone else.
Yeah. So a lot of our clients are coming to us from other companies. And for those clients, we don't really have a lot of control over what their legal setup is before, since it's just whatever they were doing with their past law firm. But for newer clients, we try to get them into a more standardized track. Yeah.
Do you have information in tables that you use information in tables or different?
You're saying, do we put the information in tables once we extract it?
Is there ever information in tables in the document?
Yes, there is sometimes information in tables in documents. And no, we don't have an official approach for dealing with that, but it's a really good idea and something that we should look into. Yeah.
So beyond a new client intake, how do you see extending this model in the practice to gone from 30 to 150 documents an hour?
Mm-hmm.
That's a pretty decent, correct prediction rate. So, and since you have humans involved in that process, you kind of almost maxed out how many documents you might be able to do an hour anyways. Yes. But how far do you see it? Much more improving, and where else will you use it in your operation?
Yeah, so right now we're at about 2/3 accuracy. Right, so if the model 2/3 of the time, it'll correctly pull out the investor name or pull out the date from the document. If we get that to literal 100%, then the paralegals can all focus on more interesting things than intake. And then the time goes to zero minutes per document. So we just want to push that as close as possible. Another thing that we want to do is get better bounds on how confident we are about a certain prediction. So even if we're not right 100% of the time, if we can be right 100% of the time on 50% of the documents, but we know which percent of the documents those are, then for those documents, we can skip the human in the loop part, and we can just go straight to the automation. And for the rest of them, we can continue to do our current thing of having a human who checks it over. Yeah. Yes. Yes. So when the humans, tell the model, oh, you were right or oh, you were wrong, that all gets recorded in a database, and Actually, that's what I'm going to be working on as soon as this conference is over, is looping that back into the model so that it has more data to work with. Yeah.
With the like 130 error rate, is that because there are like very specific things that cause a lot of problems, or is it because random which ones?
Yeah, so like what kind of errors does the model make? A lot of errors that the model makes come from the OCR. So sometimes the OCR will tokenize the word in a weird way. Like it'll have the period, like if it's $20,000.00, sometimes it'll have 20,000.00 all as one word. Sometimes it'll have it as 20,000 period 00. And in cases like that, it's a lot more likely that the model will make a mistake. And also sometimes the OCR is just wrong. Like it just won't get the right letters. The OCR is not perfect. So that's like an active area that we're looking into, is improving the quality of the OCR, maybe by like using a few different OCR things or jittering the image slightly and then combining the results of OCR on the original image and all these jittered images. So that's one area. And aside from that, it seems to have the biggest trouble with people who have like names that the model hasn't seen before. Yeah.
So you said that there are names in your model that cause your model to focus on. You have words that
Mm-hmm.
words that relative overfocus. I imagine if you're dealing with the same law firm and it's Johnson and James, whatever law firm, do you say, I don't care about Johnson and James, if you see these names, exclude them from the names that are returned, just to reduce the space of things that needs to be classified?
That's interesting. So you could basically say, like, for every client, ignore the name of that client if it appears in the document, or never return the name of a client as the counterparty in one of those client's documents.
Or don't return the law firm, or don't return that there are certain parts that we are implementing.
I got to give these talks more often because you all are coming up with some great ideas that we need to implement. Yeah.
Is this open source or any plans to open source it?
It's not open source, and our data is definitely not open source. It's like as closed as a source can be. But we use something called PyCRF suite, and that is open source. The only modification that we made to it is we basically tweaked it so that it's biased against returning these O's, and it's biased for just like freaking out and thinking that everything is an investor name. And the reason that we did it that way is that we care a lot more about our recall than our precision. So if the model's like, oh, there's like 6 different counterparties, like that's a counterparty and that's a counterparty, they're all counterparties. Because of this like PNP thing, it's a lot easier for the paralegal to be like, well, these 5 are all trash, but then this one is really good. And that's better than if it doesn't give any guesses, and then the paralegal has to just use the fail case of like looking it up themselves. It's like a cache miss. So we tweaked it a little bit to bias it against returning like whatever the most common label is. But aside from that, it's pretty standard PyCRF suite stuff. Yeah. Could you repeat that?
Have you guys considered using higher order CRFs?
Higher order CRFs. Yeah. Yeah, we have. So we have like journal club every week, and we read papers and talk about implementing them. And the most recent one we read was on these skip chain CRFs, which don't have the assumption that these different states from a long time ago don't influence them, and that's another area that we'd like to look into.
And how was the performance compared to this model?
We haven't actually tried them yet. All right, cool.